All right, today we're going to be going over the Module 4 test review. Number 1 says write an equation in point-slope form for the following line. So they give us our line, and they give us 3 points on the line. So we're going to be using point-slope form to figure out what our 3 equations are. First, let's go over what point-slope form is. So point-slope is linear, and that is going to be our y minus y1 equals mx minus x1. Now remember, you have 3 types of linear equations. You have point slope, you have slope intercept, which is the y equals mx plus b, and you have standard form, which is ax plus by equals c. So in this case, we're going to be using point slope. So let's start by finding, and remember, in point slope, we're only filling out y1, x1, and m. So first we need to figure out m. M we know is our slope. So let's start by finding the slope. So we can take any 2 points, and we want to see how do we travel from one to the next. And we always go from left to right. So I can go from this -1, 3, and my very next point would be this y-intercept here. So I'm going to use my rise over run to figure out my slope. So first I want to go down. I'm going to go down 1, 2. So I know my rise is going to be -2 because I'm going down. And my run is going to be +1 because I'm going to the right. -2 divided by 1 is going to just be -2. So I know my slope is -2. So now I'm going to take each point and I'm going to create a different equation with it. Well, the same equation for the same line. It's just going to look a little bit differently. So I'm going to start with my first one. I'm going to label this x1, y1. And I'm going to plug it into my y minus y1 equals mx minus x1. So y stays the same, minus my y1 is going to be 3 equals m is my -2, x minus -1, and 2 negatives create a positive. So that'll be my first equation. And I'm going to follow the same process for the next 2 equations. So now I'm going to look at my 1, -1. So I'm going to label it x1, y1. And I'm going to do the same thing. I start with y minus, my y1 is -1, so 2 negatives make a positive, equals -2, x minus, and then just our 1. And that is our next equation. And our last one, we're going to use the last point. We're going to label it x1, y1, and plug in the same thing. Y minus -3, 2 negatives make a positive, equals -2, x minus 2. And those are our 3 equations given the line on our graph. All right, number 2. It says write 2 parallel and 2 perpendicular equations in slope-intercept form. Awesome. All right, so we want to find 2 lines that are parallel and perpendicular to this one here. Well, first, let's figure out what our equation looks like. And if we notice, we did see slope-intercept form. So we're going to be using y equals mx plus b. So I'm going to start by finding the equation for this line. Now, I know b is my y-intercept, and m is my slope. And we always start with our y-intercept. My y-intercept in this case is -2, so I can substitute b for -2. X never changes, y doesn't change. So now I want to find my slope. I want to figure out how do I get from one point to the next point. Now here they have this point dotted, but it looks like it's in between 0 and -1. It looks like it's going to be a decimal. I'm not going to use that point. I'm going to use this point here. I know exactly what point that is, and I know exactly what point this is. I'm going to travel from left to right. So I know my rise over run. I'm going to start with up and down. Well, in this case, I'm going to be going down 1, 2, 3, down 3, and then to the right 1. So I'm going to have -3 over 1, which is just -3. So this equation represents my line. So now I'm going to start with parallel. Well, I know parallel lines have the same slope. So I'm going to find two lines that are parallel. Well, I know that any line that has this same exact slope is going to be parallel. Can't use the same line. So I'm going to write it as y equals negative 3x, and I can put plus 6, for example. Now, in this case, our y-intercept doesn't really matter because as long as our slopes are the same, you've got two parallel lines. I can also do y equals negative 3x and let's say minus 10. That is also a line that is parallel to our original. Now we're going to look at a line that's perpendicular. Well, I know perpendicular lines are opposite reciprocal. And I know to find the opposite reciprocal, I'm going to take the slope, I'm going to flip the sign, flip the fraction. So I'm going to take this negative 3 and I'm going to turn it into a positive 3. Well, not a 3, but a positive. I can write negative 3 over 1 as a fraction, and now I can flip the fraction. So my new slope is going to be positive 1 over 3. So any line with a slope of positive 1 over 3 is going to be perpendicular to this line here. So for example, I can have y equals 1 over 3x plus 6. That line is perpendicular. Or I can have y equals 1 over 3x minus 1, for example. Now, let's say we wanted to see what this looked like. If I wanted to graph this, let's say, for example, this one. I'm going to start it at negative 1, and I'm going to go up 1 over 1, 2, and 3. And if I were to graph this, I would notice that it would mean that these two lines would intersect at a 90-degree angle. And that's how I know they're perpendicular. Parallel would mean that it would never intersect. So for example, if I did an equation using 1, let's say our slope was positive 1. If I graph this, I'm going to start at 1, and then I'd go down 1, 2, 3, and then to the right 1. And if we notice, this line would also be parallel straight line, just like my other one. So this is what a perpendicular line would look like. This is what a parallel line would look like. Awesome. Let's jump to number 3. All right, number 3 says a sports company charges its customers for the following amount to ship a package. A fixed fee of $4.25 and 25 cents for each ounce in the package. So we have our fixed fee of $4.25 and we have 25 cents for each package. An equation in standard form to describe, so we're going to be writing an equation in standard form to describe the relationship between the total cost C to ship a package and the number of ounces N could be. All right, so first let's start. I like to start building my equations in y equals mx plus b form because that's what I'm used to. So we're going to start by looking at our y-intercept, which is our b. Our b is the amount that we start with. No matter how much we send, whether it's 1 ounce, 2 ounce, 3 ounce, 4 ounce, no ounces, we always have to pay that fixed fee. So that is my y-intercept because I know I have to start with the 425. So I'm going to put that as my b. Next, I have my slope. My slope is whatever is being charged over and over and over again. Well, I know my fixed fee isn't going to be changing, but I know that depending on how many ounces I buy, that's going to be a different amount. So that's going to be my slope, my 0.25. And it wants us to use N to represent ounces. And that means my C has to be my cost. So now I have my equation, y equals mx plus b form. Well, it wants an equation in standard form. That means my two variables need to be on the same side. So we have C equals 0.25n plus 4.25. And I'm going to get both my variables on the same side. So that means I'm going to move this n over to the other side. So I'm going to do opposite operation. I'm going to do minus 0.25n. Whatever I do to one side, I must do to the other. And that's going to leave me with C minus 0.25n equals 4.25. And that is going to be our equation. Awesome. Oh, and we just want to remember, standard form was our ax plus by equals c format. And we know that it's in standard form when our x and our y are on the same side. Now in this case, we didn't use x and y, but we still use the variable c and n. So we want to make sure our letters are on the same side. All right, number 4. In the coordinate plane line, n is represented by the equation 3x minus y equals 6, an equation representing a line parallel to line n that also passes through the point -1, 2 is written in the form of y equals mx plus b. What is the value of b? All right, so we need to figure out our equation in y equals mx plus b form. Now, we know we need to find b, so that's what's missing. They gave us an x and a y. That's the point that we're passing through. So we can start filling that out. We have y. Our y is going to be 2. And we have our x, which is -1. We're missing b, but we also are missing m. Now, that is where our equation that they gave us up here is important, because given this equation in standard form, I can figure out what my slope is. Now, how do we figure out our slope? We have to convert this to slope-intercept form, y equals mx plus b, in order to find our m. So I need to get y by itself. This is a y. So I'm going to start by moving the x over to the other side. We're going to do minus 3x. Whatever I do to one side, I must do to the other. I'm left with -y equals -3x plus 6. Now, I can't have a negative with my y, but I know in front of every letter there's an imaginary 1, so I can divide this by -1. Whatever I do to one side, I must do to the other. That gives me y equals 3x minus 1. That means our slope is going to be 3. Given my slope, I can plug that back in over here to solve for my b. Well, I know 3 times -1 is -3 plus b equals 2. And we're going to add 3 to both sides. And we're left with b equals 5. So my b is going to be 5. All right, number 5. The slope of a line on a coordinate plane is -2. The graph of the line passes through the point 2, -3. Write an equation in standard form. All right, let's go over again. Our standard form is our ax plus by equals c. Now, there's 2 ways you can do this. The first way is we can go from point slope form to standard to slope intercept to then standard, which is probably the way that I would prefer. Now, you could also go from slope intercept to just standard form by finding b. So I'll be showing you both ways. So first, I'm going to do the way that I would prefer, and I'm going to use point slope first. Y minus y1 equals mx minus x1. And I'm going to plug that in to my, plug in my numbers to my equation. So I have x1, y1, and m. So I'm going to use y minus -3, which 2 negatives create a positive, equals -2, x minus x1, which is 2. And I'm going to go from there. So I'm going to distribute because I want to get it in slope-intercept form. So I have y plus 3 equals 2 times -2 times x is -2x. -2 times -2 is +4. Subtract my 3 from both sides. I'm left with y equals -2x plus 1. And I want to make sure x and y are on the same side. And that's how I know I have it in standard form. So I'm going to add 2x to both sides. And I'm left with 2x plus y equals 1. That is the first way we can do it. The second way we can do it is we can plug it into y equals mx plus b to find b, plug it back in, and then put it to standard form. So I would do the same thing. So I would plug in y. My y is -3. I'm just going to draw a line here so we know the separate. Y is -3 equals m, which is -2, times x, which is 2, plus b. And then we solve for b. -2 times +2 is 4, so we have -3 equals -4, plus b. Add 4 to both sides. And I'm left with 1 equals b. Once I have 1, I can re-plug it into slope-intercept form, which is y equals -2x plus 1. Add 2x to both sides. And I have y 2x plus y equals 1. So either way, you get both answers. And for reference, this was our 4.1 notes and our 4.2 notes. So you can choose which way you were more comfortable with and then go through there. Either way, you get the same answer, which is our letter C. All right, number 6. It says the coordinate plane below shows point 1, 4, and the equation y equals -1/3x minus 1. And we want to know which equation describes a line that passes through the point and is perpendicular to the line on the graph. So first, we want to find our slope. So they gave us the slope, they gave us a graph, and they gave us the slope. So that means we can use this slope right over here, which is -1/3. And if I want to find a slope that's perpendicular to, I do opposite reciprocal, which means flip the sign, flip the fraction. So instead of a negative, it's going to turn positive, and 1/3 is going to become 3/1, which is the same as just a slope of 3. Now, I want my line to pass through the point 1, 4. So I'm going to label this x1, y1. If I notice, all my answer choices are in point slope form, which is our y minus y1 equals mx minus x1. So now I'm going to use my newfound slope, which is perpendicular to our line here, and passes through point 1, 4. So when I plug it in, I'm going to have y minus, I'm going to look for my y, which is 4, equals 3, which is my slope, x minus 1. And which answer choice matches? Well, we could have already, before we even plugged it into our equation, just by looking at the slope, we could have already eliminated A and B. And that leaves me with answer choice D. Now, if I wanted to see what this would look like, I would start at my 1, 4, and I would use my slope, 3/1, which is the same as up 1, right 1, or down 3, left 1. So from here, I'd go down 1, 2, 3 to the left 1. Down 1, 2, 3 to the left 1. If I connect my dots, that would give me a straight line that intersects, forming a 90-degree angle. And that is my perpendicular line. All right, number 7. Zara measured the height of her plant each week and graphed the data, as shown below. Which two variable linear equations suggest linear association of the height h of the plant in terms of time in weeks? So we want to look for, this is our data of our plant, we want to look for the line of best fit. We want to look at which line would best represent our data. Now, there's one of two ways you can do this. We can draw an estimate of what we think our line of best fit would look like, maybe something like this. And we could see which of our equations matches. So for example, I know that if I put my person on this mountain, this is a positive slope because we're going up the mountain. So anything with a negative slope can already be eliminated. That includes A and D. Now I can also tell that we started our slope at about 2. And I know the only one, we started our graph at about 2, so the only one with a y-intercept of 2 would be C. Now, you could have also individually graphed each line. So, for example, if we started with A, we would start at 0 because this would be as if it's plus 0. And we'd be going down to right 1. In this graph, I can't even go down 2, so I know that would have automatically been eliminated. Now, the next one would have been starting at 3, and I would have been going up 1, 2 over 1, up 1, 2 over 1, and my graph would look kind of like that. Definitely not. If I looked at C, we'd be starting at 2, going up 1, 2 over 1, 2, 3, up 1, 2 over 1, 2, 3. That one definitely looks a lot better, but we got to check D. D would have started at 0, and again, negative slope can't even go down. So that would be our C. All right, number 8. The scatter plot below shows collected data from 15 math students. The scatter plot displays a linear association between the amount of time spent studying for a test, X, in minutes and the score on the test, Y. A linear function can be used to model this association. Complete the sentences. An equation of a line that can model the association is blank. So we're looking at A first. A, we've got option 1, 2, and 3. So we're looking at which of these options best fits our data. Now, there's one of two ways you can do this. We can either draw our line of best fit, something that we think best represents our data. Now, when you're doing line of best fit, you want to see that there's about the same amount of points on either side of the line. And that's how you know you have the better line of best fit, because you want it to be pretty in between. So here, if we notice, now my line is not perfect, but we've got about 1, 2, 3, 4, 5, 6, 7 on this side, and about 1, 2, 3, 4, 5, 6, 7 on this side. So it looks pretty good. So now let's look and see which of these looks closest to my line. Now, I know it's definitely not 2 because 2 starts at 0. So I'm going to scratch that out. Now, 3 starts at 20 over here. Not quite what I'm looking for either. So we know it's going to be 1. Next says, based on the chosen model, not the data on the scatter plot, when the student spent 60 minutes studying for the test, the predicted score is about. Now, we want to see about how much students are going to have at 60 minutes. What are they likely to score? Well, I know my X was our minutes and our Y was our score. Now, it says not the data in the scatter plot. We're not using the data in the scatter plot. So what that means is we want to look at the equation that we chose. Now, we know X represents the minutes. So I'm going to take the 60 and I'm going to plug it in for X. So I have 1.5 times 60 plus 10. And we're going to take out our calculator for this one. Is our calculator. Awesome. All right, so we're going to do 1.5 times 60 times 60 plus 10. And we get 100, which is a great fit. Now, using the scatter plot, that means our scatter plot should about give us that amount. Well, let's go to 60. If I go up to 60, based on the line of best fit that I did, it looks like it does hit about 100. All right, and finally, our number 9. Which conclusion is valid? So they're giving us a graph, and it says calories burned during exercise. And we're talking about our calories on this side and our time in minutes. So the first thing we can tell is we definitely have a positive correlation. It looks like the more time we spend, as our time increases, the more time we spend exercising, the more calories we burn. So we want to look and see, based on our information here, which of these statements is true. Well, it says there is a strong negative linear correlation between calories burned and time exercising. I know that negative means it's a scatter plot going down. My scatter plot's going up, so that is not going to be our answer. An increase in time causes a decrease in calories. Well, let's check. The more calories I burn, or the more time I exercise, it looks like the more calories I burn. Because in 10 minutes, we burned about 100 calories, but in 30 minutes, we burned about 300. So our calories are definitely increasing the more time we spend. So we are going to go ahead and cross B out. It says there is a strong positive correlation between calories burned and the time spent exercising. Well, I did say that we did have a positive correlation, and it looks pretty good. It looks like our points are pretty close together, and we're going up. So we're going to leave that one just in case. And it says a decrease in calories causes an increase in time. Well, our calories go down. Let's say at 500 calories, we worked a total of 50 minutes. If we go down in our calories, 300, it looks like we exercise for less time. So we do not increase our time. So our answer is going to be C. And that is it for our Module 4 test review.